19, which he took at Liverpool John Moores University. It's now moved on to a Royal Society Dorothy Hodgkins Fellowship at Sheffield. And the title of his talk is The Origin of the Galactic Field, Where Are the Suns Born?
Thank you very much, John. Good evening, everybody. So what I'm going to try and do is summarize the work that I carried out during my RAS fellowship at Liverpool. One of the sort of central questions we're trying to address in this is, where are most stars born? Now, if you look at young stars, we know that a fraction of them are found in very, very dense clusters, anywhere between 100 to 1 million stars per cubic parsec. This is the closest star cluster with very massive O-type stars to the Sun. This is the Orion Nebula cluster. And even further away in the Large Magellanic Cloud, you have R136, and this hosts the most massive stars that we know about in the universe. So we know that some stars are in dense clusters, but we also know that there are some stars that are in less dense, more quiescent or diffuse regions. These are sometimes referred to as associations. This is rather just like a historical terminology. But typically, these would have densities between 1 and 100 stars per cubic parsec. Now, the Sun today sits in an environment where the stellar density is only 0.1 stars per cubic parsec. So the point is young stars are always in regions of higher density than we're in today. Why is it important to figure out what the density that most stars form at is? Well, if you look at observations of galaxies other than the Milky Way, we know that the star formation rate in those galaxies is much lower than what we would naively expect if we were just to convert some of the gas into stars. And the reason that's often cited for this low star formation rate is the presence of feedback in these star form regions in these galaxies. And this is a plot showing the effect of feedback as a function of distance from the center of the R136 cluster that I just showed in the previous slide. And so one of the posits of this theory is that for you to have the required star formation rates we see in other galaxies, then most star formation has to be in very dense star forming environments. On the other hand, if we look at the distribution of exoplanetary orbits and compare those to the orbits of the solar system, changing topic somewhat, but the two are linked, we see that compared to the solar system, the orbits of extrasolar planets are very, very different most of the time. So the solar system planets are shown in red here, and we see that there are a significant number of planets that have very high eccentricities, anywhere between 0 and 1. And furthermore, there are a lot of planets that are very close into their host star, so sub-Mercury orbits. And what is strange about this observation is that a lot of these objects are Jupiter mass or more. And conventional planet formation theory tells us that you can't form Jupiter mass planets at such close distances to the star. So some mechanism has moved them closer to the star. Why is this related to the star formation environment? Well, we know that planet formation basically happens at the same time as star formation. This is a plot of the fraction of young stars that host a protoplanetary disk as a function of their age. And you can see that after about 5 million years, almost no star has a disk that's observable in the infrared. And the interpretation of this decrease in disk fraction is that either the disks are being destroyed completely or you're already forming planets. And there's been some observational evidence to corroborate this recently. This is the beautiful HL Tor image from ALMA. And this is a star that's about 1 million years old, and it has a protoplanetary disk. And you can see that there are lines in the disk. And so one interpretation of these lines is that these are planets that have already formed that are sweeping out gaps in the disk. And as I mentioned a few slides ago, at this stage, the stellar density is way in excess of that in the solar neighborhood. Why is that important? Well, you have to worry about interactions with other stars at these high densities. So these are the results of an N-body simulation where you show eccentricity against semi-major axis, and initially all the planets are placed at 0 eccentricity, so a perfectly circular orbit. And after 10 million years in a star cluster environment, you have eccentricities anywhere between 0 and 1. Some of the planets have moved closer to their host star, some of them are scattered further out. You also increase the inclination of the planets, anywhere up to 180 degrees. And just to remind you all, the solar system is flat in inclination. So these planets really have quite a violent upbringing. Furthermore, 10% of the planets become stripped from their parent star altogether and become free-floating in the star cluster, or they're ejected from the star cluster altogether. So in order to understand whether or not a majority of planetary systems undergo these very dynamic, violent processes early on in their life, we need to know what the star formation environment typical density is in the Milky Way, and if you want to take it further, in other galaxies. However, there's a problem. You can't simply just look at the present-day density of a young star-forming region and then infer the number of dynamical interactions, the likelihood of a planetary system being disrupted in that star-forming region. For the reason that when you have a very dense star cluster, that tries to relax over time. So the stars interact with each other, and the motion of that cluster is for it to expand. And the expansion is actually quite rapid. So these are star clusters, again, n-body simulations shown by the gray lines, with initial densities around 10 to the 4 solar masses per cubic parsec, so the density of a globular cluster or thereabouts. You can see that over time, the density rapidly decreases, so that after 5 million years, you've decreased the density by several orders of magnitude. There are models that posit that these observed star clusters started off with much, much higher stellar densities. However, the degeneracy problem in all of this is that if you were to start these star clusters with much lower densities, you can see that the observations are consistent with either much, much higher stellar densities initially, or actually rather moderate stellar densities initially. So how do we get around this problem? Well, we model these star-forming regions using n-body simulations. So this is an n-body simulation of a star-forming region set up with spatial and kinematic substructure. These are informed by observations of very, very young star-forming regions. And what's going to happen over time is that star-forming region is going to relax, the substructure is erased, and what you see is the red points, they're the most massive stars in the star cluster, they tend to sink towards the center of the star cluster, and this is a process called dynamical mass segregation. You'll notice that we completely erase all of the initial substructure so that we're left with a rather smooth, centrally concentrated morphology. What we want to do, though, is instead of just looking at the animation, we want to try and quantify this evolution. So the way we do this is a graph theory approach. So we use minimum spanning trees. This is the graph that connects all the points in a distribution via the shortest possible path length with no closed loops. And we take the average of these minimum spanning tree lengths and then divide it by the average separation length between the stars. So it's a slightly different measurement. But when you take that ratio, you get what we call the Q parameter. And you can see for the end point of that simulation, where we've got rid of the substructure and it's got a smooth morphology, this Q parameter is about 1.1, 1.2. But then if we look at the initial conditions of that simulation, where we've got a lot of hierarchical substructure, the Q ratio is much, much lower. It's around about 0.4. And there's a boundary between substructure or self-similar hierarchical spatial distribution and smooth centrally concentrated distribution at a value of around Q of 0.8. So how can we use this to interpret our simulations? Well, this is the initial conditions of the simulation. This is the simulation after 5 years. And we just look at the evolution of the Q parameter. So again, below this 0.8 value, you've got spatial substructure. Above the 0.8 value, you've got smooth or centrally concentrated morphology. And the simulation, over time, loses its substructure, and this is shown in the Q parameter. And we can evolve that simulation 10 times, change the random number seed, just so we get an idea of the inherent stochasticity in the dynamical evolution. And what you see is all of these clusters with the same initial conditions generally follow the same behavior. So this immediately allows us to put constraints on this density degeneracy problem. So let me remind you, we start off with some simulations where we put very, very high stellar densities initially. These are consistent with these observations after a few million years. But if we look at the Q parameter for these same observed regions, then what we see is the majority of the observations lie much lower than the simulations of these dense initial conditions. So these dense initial conditions in the simulation are inconsistent with the observations. Apart from perhaps this point here, that's the Orion Nebula cluster that I showed earlier on in the talk. So In the local solar neighborhood, we're probably looking at half of all star formation occurring in moderately low density initial conditions. And just to demonstrate this point a little bit further, if I start with lower initial densities to begin with, then the simulations are much more consistent with the observed star forming regions in the local vicinity of the sun. So that's one diagnostic that we've been exploring, but that just quantifies the evolution of one type of initial conditions for our simulations. So what if the star forming region expanded to begin with? Okay, so there's a theory a few years ago that was very popular that the gas left over from star formation, when that's removed by supernovae explosions and stellar winds, causes an immediate expansion of the star forming region. And this is what this simulation tries to mimic. So what you'll notice here is the massive stars, shown in red, rarely interact with each other because they're being pulled apart from each other over time. You see that the region as a whole expands, but the most massive stars tend to just collect little retinues of low-mass stars. So how does that evolution look when we quantify it using our structure parameter Q? So again, these are the initial conditions. We've got substructure. The region expands, but you freeze in a lot of that substructure. And you might say to me, okay, well, that star forming region is expanded by a factor of 10, but we know from looking at star forming regions that they have a range of sizes, a range of dynamical scales. So this really allows us to place constraints on the initial conditions of these star forming regions. And so if we look at it with the Q parameter, start off with substructure, and then we retain it for the duration of the simulation. And again, if I look at an ensemble of simulations with the same initial conditions, we get very similar behavior. But you'll notice that there's a few simulations here that are kind of on the border, okay? And we're worried about them, so we want to try and take this analysis further. I should add that this Q parameter is not completely magic. It doesn't really distinguish between very different morphologies, okay? It'll tell you if something's substructured or not, but you can see these regions all have the same Q parameter, give or take, and they've got very different morphologies. So there's still a lot of work to be done in quantifying the statistical spatial distributions of these types of star forming region. In order to try and make our results more robust, we then started looking at the relative spatial distribution and the relative location of the most massive stars in the star forming regions with respect to low mass stars. The first thing we looked at is the surface density. So this is just sitting on a star and going out to a certain number of nearest neighbors and then working out the local surface density around each star and plotting it as a function of the stellar mass. So this is a relatively easy thing to do observationally. And then you'll get a median density for the whole star forming region, shown by the blue dashed line. And then maybe the most massive stars have a different spatial distribution. Maybe the brown dwarfs have a different spatial distribution. And we can then quantify the differences in these distributions and add a statistical significance to it. And all I'm going to show you in the next few slides is we're going to divide the line, the median surface density of the most massive star by the median surface density of the star forming region as a whole. So this is what happens in the n-body simulation. So again, very dense initial conditions to begin with. And the most massive stars to begin with are not in regions of higher than average surface density. After a couple of million years, the star forming region has relaxed and the density is decreased by a couple of orders of magnitude. But you can see that the most massive stars are in regions of significantly higher than average surface density. And this, in that simulation, is because they all sank to the center through dynamical mass segregation. We can plot this evolution over time, and it's always significantly above unity, the difference between the most massive star's density and the surface density of the remaining stars. What can we do with this? Well, we can then incorporate the information that we have using the Q parameter. So this is structure versus the relative surface density of the most massive stars. So Q parameter here, again, below this horizontal red dashed line is substructure, above it is smooth, and relatively higher than average surface densities going to the right in both plots. So these are the initial conditions of the simulations, and then after 1 million years and 5 million years, the observations of some nearby star forming regions are shown by the blue points, and these are all with ages about 1 to 5 million years. So they should be compared to somewhere between these values here. So what you can see is, again, with the possible exception of the Orion Nebula Cluster, most nearby star forming regions probably weren't as dense as the initial conditions we have in the simulation. If we then look at the expanding scenario, we also see that the simulations are inconsistent with the observations because what happens is, even though the substructure was frozen in, so we're always keeping below this line here in this plot, the most massive stars sweep up retinues of low-mass stars and have higher than average surface densities. So we don't think that most star-forming regions pop and expand very, very quickly. Okay? What is consistent with the observations are simulations that are much less dense than our fiducial models. Okay? So around about 100 stars per cubic parsec. And what you see here is that most of the observations in the local solar neighborhood are consistent with densities of probably about 100 stars per cubic parsec to begin with. Now, that's just looking at the spatial information that we have in the star-forming regions. There are various ground-based surveys that have been taking data for the last few years that are measuring the radial velocities in star-forming regions and getting very, very accurately determined velocity dispersions. Once you've got a velocity dispersion, you can compare that to the velocity dispersion that you would expect if the star-forming region were to be in virial equilibrium, so static, not expanding, not contracting. But to quantify this, you need to have some idea of the mass that's enclosed within a certain radius r, and you've also got to say something about the structure of the star-forming region. So that's where the previous work that we've been doing comes into this, because we can estimate this to a reasonably high degree of accuracy. There is a problem, however. In the simulations that I showed of the star-forming regions that collapse, you start off with subvariable velocities, and you collapse, all the stars interact with each other, and then you have a velocity dispersion that plateaus out at about 1 kilometer a second. However, the velocity dispersion that you'd estimate for the region to be in virial equilibrium from this simple formula gives a velocity dispersion down here. Okay? So that's telling us that the regions are highly supervirial, so they're expanding. Unfortunately, that's not the whole story. If you measure the virial ratio directly in the simulations, then you see that you start off subvirial, there's a collapse and a bounce, where the region is supervirial for a short period of time, but then it relaxes to go to somewhere that's roughly in virial equilibrium. This one-dimensional measure of the velocity dispersion that we use observationally to infer the virial ratio would tell you that that region is highly supervirial. So the point I'm trying to make here is you can't just estimate the bulk motion of a star-forming region from one measurement. You need to incorporate information from the spatial distributions as well as the kinematic distributions. And this is something that Gaia is going to help us with as well, because we're going to get proper motions of stars on the outskirts of star-forming regions and say something about how many stars are ejected and at what velocity. We can compare our simulations to some of these observations that I mentioned. So one of the exciting results that's come out of some of these surveys is that the pre-stellar cores appear to have a velocity dispersion that's consistent with subvirial velocities, so collapsing, and the pre-main sequence stars have a velocity dispersion that's consistent with them being in virial equilibrium. So perhaps this interpretation here that we start off subvirial and then we reach something that's in virial equilibrium that we can then confirm from comparing the data to simulations is not a million miles away from reality. So, just for the last couple of minutes, I'd like to tell you a little bit about how I think our own sun fits into all this picture and what we can say about the solar system. You may know that some meteorites from the epoch of planet formation around the sun have very short-lived radioactive isotopes within them, or at least the daughter products of these radioactive isotopes. And that suggests the sun was probably born in proximity to a very massive star that exploded as a supernova. Now, there's a bit of debate at the moment in the literature about whether or not the sun formed from pre-enriched material from the supernova, or whether the sun's protoplanetary disk captured some material from a supernova that exploded. In order to get a 25 solar mass star, on average, you typically require around 2,000 other stars, and this has been cited as being a very improbable astrophysical condition for the formation of the solar system. But we can look at this in more detail. So a student of mine, Rana Nicholson at LJMU, here she's plotting the cluster mass function. So this is simply the number of clusters as a function of their mass, and it has a -2 power law overall. So a cluster that's around about 2,000 stars would sit here. Now, a low mass cluster very rarely would form a massive star. However, there are far more low-mass clusters than there are high-mass clusters, and so the number of low-mass clusters that are unusual in that they form a massive star is actually much, much higher than these 2,000 star clusters that the sun is posited to have formed in. So in terms of the mass budget that we need to form stars and get a supernova explosion that would enrich the solar system, I don't think there are any constraints on the mass of the star-forming region. And then another student of mine, Tim Lichtenberg in ETH Zurich in Switzerland, is doing a PhD that's part geophysics, part astrophysics, and he's looking at the radiogenic heating that these isotopes produce in planetesimals that go on to form planets like those in our solar system. And Tim's result is that the amount of radiogenic heating you get in a typical star-forming region is completely consistent with the values you'd expect in the solar system. So it's good news in the sense that there's not an astrophysical anomaly in where the sun formed in a star-forming environment, but it's bad news in the fact that a few years ago, we thought this could constrain quite nicely the type of star-forming environment that the sun would have formed in. And unfortunately, we seem to have opened up the parameter space a little bit here. So I'll just conclude. We're trying to understand where and how most stars and, by extension, planets form. We're trying to couple observations with simulations to really understand the initial conditions of star formation. And one of the results that's come out of this is most star-forming regions have much lower initial densities than previously thought. So perhaps planet formation actually goes on unhindered in these star-forming regions. And maybe the sun's birth environment was normal. So I'd just like to finish by thanking the RAS for giving me the sponsorship for a fellowship for 3 years, and thank you for your attention today. Thanks a lot.
So, time for a few comments and questions. Ian?
Thanks. Yeah, so the other thing that's interesting is the sun's planets are in much more circular orbits than some of these other systems. So is that consistent with your argument that the cluster in which the solar system formed may not have been very massive?
Yeah, so I think the density in which the sun, most stars in the local solar neighborhood form could disrupt maybe 5% of planetary systems, 95% obviously unscathed. So I think the solar system is not inconsistent with that.
So, it sounds as if everything is completely clear. Richard, thank you very much indeed.